Hi folks, welcome to chapter 12. In this chapter, we are going to be looking at acids and bases. Let's start an introduction to acids and bases. Each time when we hear of acids, we think of substances that can burn our skin, they can destroy our clothes, and they can cause more havoc. So here, we have substances that are actually acidic. So we have like the mandarin, we have vinegar, and we have the soda. All of these substances are acidic. We also have other substances that are bases, like the baking soda, it's a base. So what makes them different from the concept of the acids that we know that they destroy and they can burn our skin? So we are going to describe acids and bases in terms of strength and concentration. So by the end of this lesson, you'll be able to explain why the acids that we know, like the concentrated sulfuric acid, they will destroy, and the acids that are found in vinegar, mandarin, or sodas don't destroy. So we are going to look at the definitions of acids. We are going to look at two very important definitions of acids, and the first one that we are going to start with is the Arrhenius definition. So we are going to look at the Arrhenius definition of acids and bases. Now, Arrhenius defines an acid as a substance that produces hydrogen ions in water. So here we have the generic way of writing an acid. Whenever you see Ha, that indicates that the substance is an acid. So it means that when Ha is dissolved in water, it produces the hydrogen ion and this anion. Let's look at an example. If we take hydrochloric acid, we dissolve it in water, it's going to produce the hydrogen ion and the chloride ion. Now, Arrhenius defined a base as a substance that produces hydroxide ions in water. So the general equation is MOH to give us the M cation and the hydroxide anion. Let's look at an example here. If we use potassium hydroxide, we see that we dissolve in aqueous solution to give us potassium ion and the hydroxide ion. Now, when we put the HCl, the hydrochloric acid, when we dissolve it in water, we see that the hydrogens are attracted to the oxygen and the chloride are attracted to the hydrogens. So there is that stabilization by the water molecules. So in the situation where we dissolve the hydrochloric acid in water, it can actually give us what we call the hydronium ion. Here you will have H3O, like you will see in this equation here. So if you dissolve hydrochloric acid in water, it produces the hydronium ion and the chloride ion. So this is the chloride here is stabilized by the hydrogen. So this is called the hydronium ion. Now let's look at two ways to show acids in water. We can show acids in water in two ways. The first way is like you take hydrochloric acid, if you dissolve it in water, it's going to produce a hydrogen ion, which is called a proton, and the chloride ion. As well, you can say in the presence of water, you include water in the equation. So in the first equation, we did not include water. So in the second equation here, you include water in the equation. So we see that the hydrochloric acid is going to produce the hydronium ion and the chloride ion in water. So the hydrogen ion here is called a proton in this first case, and this is called the hydronium ion. Now let's look at this example here. Show how nitric acid ionizes in water. So for us to show how nitric acid ionizes in water, we are going to use two ways. Remember, in this in this situation here, we said there are two ways. So we are going to use the first way and the second way where we include water. So in the first case, we are going to do it where water is not included. So we have nitric acid decomposing to give us the hydrogen ion plus the nitrate ion. That is the first scenario here. In the second scenario, we have water included in the equation. So when water is included in the equation, we are going to form a hydronium ion instead of a hydrogen ion in this case. So we have nitric acid dissociating in water to give the hydronium ion and the nitrate ion. So these are the two ways that we can show the ionization of nitric acid in water. Now let's look at polyprotic acids. So what are polyprotic acids? Polyprotic acids are acids that contain more than one hydrogen ion. So polyprotic acids can release more than one hydrogen ion into aqueous solution. For example, if we take sulfuric acid has two hydrogen ions and it can actually release the two into solution. Now in the first ionization here, we are going to obtain a hydrogen ion and a hydrogen sulfate ion. So that is the first situation. In the second ionization is the hydrogen sulfate or the bisulfate that is going to release the other proton to form the hydrogen ion and the sulfate ion. So we have seen monoprotic acids. So the hydrochloric acid, hydrobromic acid, and nitric acid are monoprotic. Mono means only one. Protic means they can release hydrogen. So mono means they can release only one hydrogen in solution. So these are monoprotic acids. So diprotic acids are the ones that contain two hydrogen ions. So we have sulfuric acid and we have carbonic acid. We also have a triprotic acid. So triprotic acids, they have three protons that they can release into solution. So any acid that has more than one proton that can be released is called polyprotic. And the acid that has just one, they are called monoprotic acids. Now, we have looked at the Arrhenius definition of an acid. We are now going to look at the second definition of acids and bases, which is called the Bronsted-Lowry definition. So, how does Bronsted and Lowry, how did they define acids and bases? So, let's look at the equations that we have here. In the first equation here, we see that this is hydrochloric acid dissociating into water to give us the hydronium ion and the chloride ion. In the second equation here, we have hydrochloric acid reacting with ammonia to give us the ammonium ion and the chloride ion. So, according to the definition of Arrhenius, Arrhenius does not recognize ammonia here as either a base or an acid, because according to Arrhenius, an acid will release hydrogen ions in solution while a base will release hydroxide ions in solution. So ammonia here cannot be recognized as a base because it does not contain hydroxide ions. That is according to the Arrhenius. Now we are going to see what Bronsted and Lowry says about this situation. So in the first case here, we know that the hydrochloric acid is the acid, and for Bronsted-Lowry, they define an acid as a compound that donates hydrogen ions. So in this first case, we see hydrochloric acid donating the hydrogen ion to water, and the water now to form the hydronium ion and the chloride. Now, for the base, the Bronsted-Lowry defines a base as compounds that accept hydrogen ions. So the water here is a base because it would accept the hydrogen ion to form the hydronium ion. Now, let's see the second case here. Is this an acid-base interaction? Alright, we know that hydrochloric acid is an acid. Now, what about the ammonia here? the ammonia is going to accept a proton to form the ammonium ion. So ammonia here will be a base. So water here is the base and ammonia here is the base. So according to Bronsted-Lowry, a base is a proton acceptor. And we see here that ammonia accepts a proton to form the ammonium ion. Now, let's look at what we've just seen here in detail. The reaction here of hydrochloric acid and water and ammonia and hydrochloric acid. So the one for water and hydrochloric acid, the oxygen here is going to attract the proton, and that gives us the hydronium ion and the chloride ion. And for the reaction of ammonia and hydrochloric acid, the nitrogen is going to pick up the proton, the nitrogen accepts the proton, and that gives us the ammonium ion and the chloride ion. So here we will see that this is the acid because it gives the protons, and here these are the bases because they receive the proton. Now let's look at this case here. So the equation here is the reaction between ammonia and water to give the ammonium ion and the hydroxide ion. So acids are compounds that donate protons and bases are compounds that accept protons, as we have said. Here the ammonia here is the base and it gives the ammonium. So this is a base because it accepts the protons. And here water is the acid because it donates the proton. When it donates the proton, it forms the hydroxide ion. Now let's look at how we can identify the acids and the base in this reaction. Which one is the acid here and which one is the base? So this is hydrosulfuric acid and this is water. How can we identify which is the acid and which is the base? Let's look at the product. Here we have hydrosulfuric acid, and if we look at it to the right, we have the bisulfite. So the bisulfite here, we can see that the hydrosulfuric acid has lost a proton, so it has donated a proton to become hydrogen sulfide or the bisulfite. So this is the acid. And for the water molecule here, we see that the water molecule has accepted a proton to form the hydronium ion. So the species that accepts a proton is a base, and the species that donates a proton is an acid. So the hydrogen sulfide, the hydrosulfuric acid here is the acid. Now let's look at a summary of the Arrhenius and Bronsted-Lowry definition of acids and bases. We've said Arrhenius defines an acid as a substance that produces hydrogen ions or hydronium ions in water, and a base as a substance that produces hydroxide ions in water. For Bronsted-Lowry, acids are substances that donate protons and bases are substances that accept protons. Now let's look at acid-base equilibrium reactions. We are going to see the strong acids and weak acids here. Now, before we continue, we need to know what is a strong acid and what is a weak acid. Remember, I said from the beginning of this lecture that we are going to be defining acids based on their strength and concentration. So now we are looking at the strength of an acid. What is a strong acid and what is a weak acid? So a strong acid is a substance that completely ionizes in water. So if you put a strong acid in water, it will ionize completely. So we have 7 strong acids that exist that you should know. So these are the 7 strong acids. We have hydrochloric acid, we have hydrobromic acid, we have hydroiodic acid, we have nitric acid, we have sulfuric acid, we have perchloric acid, and we have chloric acid. So any other acid out of these acids is a weak acid. Now let's look at weak acids. What is a weak acid? Weak acids are substances that ionize only partially in water, so they do not completely ionize in water. For example, here we have hydrofluoric acid. Hydrofluoric acid will dissociate only by 2%. So if you put hydrofluoric acid in water, you are going to have the hydronium ion and the fluoride. So you will still have 98% of hydrofluoric acid without being dissociated and only 2% of the fluoride. So what you see here for the weak acids, you will always see an equilibrium reaction. So it shows that the reaction goes both in the forward and the backward direction. So weak acids will always be denoted by a double reaction where you see the equilibrium by the equilibrium reaction. Now let's look at the acid-base equilibrium reactions. Here we have a way. So we are looking at them for weak acids. This equation that we see here, we can look at it in two ways. We can look at the equation like from left to right. So water reacting with hydrofluoric acid to give the hydronium ion and the fluoride. And the second way, we can look at it from the right to left. That is the fluoride reacting with the hydronium ion to give hydrofluoric acid and water. So we are going to be able to identify the acid and the base in the forward reaction, and we are going to identify the acid and the base in the backward reaction. So for the forward reaction, the water is going to accept the proton from the hydrofluoric acid, and we know that a base is a proton acceptor while an acid is a proton donor. So here the hydrofluoric acid is the acid and water is the base. Now that will give us this product of the hydronium ion and the fluoride. Now if we look at the reaction from the left, we'll see that the fluoride is going to pick up the proton from the hydronium to form hydrofluoric acid, which means that the fluoride receives the proton and the hydronium ion donates the proton. So the proton acceptor here is the base and the proton donor is the acid. So everything here will be the conjugate. So the acid here is called the conjugate acid, and the base here that receives the proton is called the conjugate base. So we are going to see acid base pairs. So as we move ahead, we'll see acid base pairs. So we see here the base here we have the conjugate acid. For water here it becomes a conjugate acid. When it receives the proton from the hydrofluoric acid, it becomes a conjugate acid. And we see hydrofluoric acid here, when it donates its proton, it becomes the conjugate base. Now let's look at this other reaction. So we have to bring out the acid base conjugate here in this reaction. Here is the reaction of trichloroacetic acid with water to form hydronium ion and the trichloroacetate ion. So here the trichloroacetic acid is the acid and this is the conjugate base, because the acid and the conjugate base differ only by the absence of the proton in the conjugate base. So what you see here is the acid, you see there is a proton, there is a hydrogen, and in the conjugate base there is that absence of the hydrogen. So the acid and the conjugate base, they differ only by that hydrogen that is not present in the conjugate base. So we call this the trichloroacetic acid and the trichloroacetate ion, the conjugate base pairs. We call them acid base pairs. So here we have water. As the acid donates the proton, the water accepts the proton to form the hydronium ion. So the hydronium ion here is the conjugate acid. So water is the base, the hydronium ion is the conjugate acid. So they also form an acid base pair. Now an analogy for you to understand the acid base conjugate pairs. For example, here we have a dog and a cat. the duct here has a hydrogen ion. When the duct donates the hydrogen ion to the cat, the duct now becomes the conjugate base. And the cat here, when it accepts the proton, it becomes the conjugate acid. So here's the acid duct, and here is the conjugate base duct. So here we have the cat, which is the base, and here we have the conjugate acid. Now, a conjugate base is identical to the acid, but without the hydrogen. Look at the duct here. It is identical. You see the conjugate base here is identical to the acid, but the conjugate base does not have the hydrogen, the proton. So that is the difference between the conjugate base and the acid. Just the presence or the absence of that hydrogen ion. Now, let's look at the acid-base reactions and drug molecules. So drugs, both illegal and the legal, they undergo acid-base reactions. Now, we are going to look at this two scenarios here. We have this formula here, as you see this compound. This is the formula of cocaine, and this is the powder form of cocaine, and it is the acidic form. So this is the acidic salt, or is called powder cocaine. Now, when it undergoes an acid-base reaction, here, this is the conjugate base of this acid. So when that happens when you react this with a base. So the base will act like a proton acceptor. It will accept that proton, and we are left with a conjugate base here. So this conjugate base is the base form, the free base form, and this is what is called crack. Now the tobacco industry, the cigarette industry as well, they use the acid-base reactions. So tobacco contains nicotine. So what the cigarette companies do, they react the tobacco with ammonia. The tobacco is acidic, so when they react it with ammonia, it forms the free base. So it forms the free base nicotine. This is nicotine. This reaction leads to the consumption of the nicotine in high amounts, which leads to addictive behavior, and smokers have the tendency to keep smoking, and that is how they keep selling the cigarette products. Now, let's look at this practice problem. Identify the acid-base pairs in the following equilibrium reaction. So we have hydrobromic acid here, and the reaction here, we have the acid, as we already know, hydrobromic acid. This is the acid, this is the base here, because it's accepting the proton from hydrobromic acid to form this ion. So in this case, the hydrobromic acid is the acid, and the conjugate base is the bromide. And this is the base, because on each side we always have the acid and the base. So on the left side, we've already identified the acid, which is hydrobromic acid. So this is the base. And on the other side, we always have the conjugate base and the conjugate acid. So if this is the base, then this is the conjugate acid. So that is how you identify the acid-base pairs. Just being able to identify one of them will be easy to identify the rest. Just like we identified hydrobromic acid as the acid, you already know that the conjugate base will be different from this just by the proton. So when you look at it here, you already see that the conjugate base will be the bromide ion. So you've already identified the acid and the conjugate base. So that helps you to identify the other one. Since we can always have just an acid and a base, therefore this is the base and this is the conjugate acid. Now, there is a question that you should answer. Are conjugate bases basic? For us to answer that question, let's start with this equation for hydrofluoric acid reacting with water to give the hydronium ion and the conjugate base. So we have the conjugate base here. So Is this conjugate base basic? Alright, let's look at the second equation here. We have the fluoride accepting a proton from water to form hydrofluoric acid. So the fluoride, for it to be able to accept a proton, it means that it is a base. So the fluoride is a weak base that accepts a proton from water to form the hydrofluoric acid. So conjugate bases are basic. Now let's look at the acid-base behavior of the conjugate acids and bases. We have this acid here, hypochlorous acid, and here we have this base. Now in this reaction, we have the hypochlorous acid reacting with water to give the hydronium ion and the ion here. Now if we take this as the base and react it with water, we are going to have the conjugate acid, which is the hypochlorous acid. Now what you observe here is that the conjugates of the weak acids are bases. So this is the weak acid, the conjugate here is the base, and this is the base that we have here. The conjugate, when we react that base, the conjugate of the base is a weak acid. Now let's look at the reactions that involve acids and bases. For the reactions that involve acids and bases, we already saw one of the reactions, which was the neutralization reactions in chapter 6. So we are going to be looking at 3 reactions of acids and bases here. The first reaction will be the acid-base neutralization reaction that we already saw. The second will be reactions of acids with metals, and the third will be the formation of acids from non-metal oxides. So let's start with the first reaction, which is the acid-base neutralization reactions. Now, acids and bases react to form a salt and water. Remember, salt here refers to an ionic compound. So any ionic compound is called a salt. Salt is not sodium chloride. So whichever compound you see that is an ionic compound is called a salt. So now let's look at an example here. We have hydrofluoric acid in this neutralization reaction reacting with sodium hydroxide. That is going to form water. So the hydrogen here from the fluoride, from the hydrofluoric acid, and the OH from the sodium hydroxide will form water, and sodium fluoride. So sodium fluoride here is the salt and the water. Now another example is the perchloric acid. Perchloric acid here reacting with potassium hydroxide to give us water and potassium perchlorate. Now this is the neutralization reactions that we've seen. What is the driving force for these neutralization reactions? As we already saw in chapter 6, the driving force for the neutralization reactions is the formation of the water molecule. Now let's look at the acid-base neutralization reactions in terms of the molecular equation, the total ionic equation, and the net ionic equation. So the equations that we've seen here, these are the molecular equations that we've seen. So the molecular equation for the reaction of the perchloric acid with potassium hydroxide to give water and potassium perchlorate, we call this the molecular equation. Now let's see the total ionic equation. For the total ionic equation, this is going to dissociate into its ions, this into its ions, and this into its ions. Remember, the solid, the liquid, and the gas, they do not dissociate when we are talking about the total ionic equation and the net ionic equations. So for the total ionic equation, only the perchlorate here, the perchloric acid will dissociate, the potassium hydroxide will dissociate, and the potassium perchlorate will dissociate. That gives us the hydrogen ion plus the perchlorate ion plus the potassium ion plus the OH ion, the hydroxide, to give us water. Water here is liquid, so it doesn't dissociate. So solids, liquids, and gases do not dissociate, I repeat. Now, we have the potassium ion and the perchlorate ion. So we said for us to obtain the net ionic equation from the complete ionic equation, we cancel out what appears in both sides of the equation. So we have the potassium here and the potassium here. We cancel that out to obtain the net ionic equation. We have the chlorate here, the perchlorate, and we have the perchlorate. And for the net ionic equation, we are going to obtain hydrogen reacting with a hydroxide to give us water. Remember, the states here of the ions are aqueous because they are in solution. They are always going to be aqueous. So that is how we get the total ionic equation from the molecular equation, and then the net ionic equation from the complete or total ionic equation. So the formation of water drives the neutralization reactions. So the driving force for neutralization reactions is the formation of the water molecule. Now, let's look at this practice. Write a balanced equation to show the reaction of aqueous nitric acid with aqueous calcium hydroxide. So we already saw how to write the formula of compounds and how to balance reactions. So this is an easy one. Now, we have nitric acid, which is aqueous, plus calcium hydroxide, which is aqueous. That is going to give us salt and water because it's a neutralization reaction. So what is the salt that we are going to obtain? We are going to obtain calcium, nitrate, and water. So now, let's see if the reaction is balanced. The equation is not balanced. We have one nitrate here to the left, and we have two nitrates on the right. We have 3 hydrogens here because the hydroxide here does not appear on the right. We have to look at it in terms of oxygen and hydrogen. So we have 3 hydrogens here to the left, and we have just 2. We have 2 oxygens here, and we have just 1. So let's start by balancing the nitrate. We have 2 nitrates to the right and 1 to the left. So if we put a 2 here, that balances our nitrate. And if we look at it now in terms of hydrogen, we see that we have 2 hydrogen plus 2, that makes 4. And we have only 2 hydrogens here. So we have 2 oxygens and we have only 1 here. So if we put a 2 here, the equation is not balanced. So we have the balanced equation for the neutralization between nitric acid and calcium hydroxide. Now, the second type of reaction that we are going to see, the first one was the neutralization reactions. The second reaction of that we are going to see are the reactions of the acids with metals. Now, most metals will react with acids to produce metal cations and hydrogen gas that is always given off. So when the reactions of metals with acids, you will always see a fizzing sound, which is the hydrogen gas given off. So the molecular equation here for the reaction of iron with hydrochloric acid, this is a balanced equation. We see iron reacting with hydrochloric acid to give the metal chloride here plus the hydrogen gas. So the net ionic equation in this case, remember I said the net ionic equation or the total ionic equation, the species that only break down are the ones that are aqueous. The solids and the liquids and the gases, they do not break down. So let's write out the total ionic equation here. For the total ionic equation, we are going to have iron solid plus, since hydrochloric acid here is aqueous, we are going to have 2 hydrogen ions aqueous plus 2 chloride ions aqueous to give us, since the iron 2 chloride here is aqueous, so it's going to dissociate to give us iron 2 plus aqueous plus 2 chloride ions plus the hydrogen gas. Now, we said to obtain the net ionic equation from the total ionic equation, what appears on the left and the right will cancel out. So the only thing that appears on the left and the right here are the chloride ions. So we cancel out the chloride ions. And the net ionic equation will be ion solid plus 2 hydrogen ions aqueous to give us the ion 2 plus aqueous plus hydrogen gas. Now, let's see another example. Now, let's look at what we call precious metals. So, precious metals are metals like silver, gold, and platinum. And the precious metals do not react with acids. So, precious metals, we call them precious metals because they are rare and they are not reactive with acids. So, here in this test tube, we have gold placed in a solution of hydrochloric acid, and it does not react. So the precious metals, they are called precious because they are rare. They do not react with chemicals, and they are precious. They are beautiful. So here, this is gold, and it's not going to react. So they are not reactive. So let's look at the third type of reaction, which is the formation of acids from non-metal oxides. So the non-metal oxides are compounds that contain non-metals bonded to oxygen. So an example is carbon dioxide. So the non-metal oxides often react with water to form acids. So if we take carbon dioxide and react it with water, that gives us carbonic acid. So this is an example of a non-metal oxide. So other examples of non-metal oxides could be the sulfur dioxide and the nitrogen oxides. So the sulfur oxides and the nitrogen oxides, those are other examples of non-metal oxides. Now, formation of acids from non-metal oxides continue here with the sulfur oxides and the nitrogen oxides. Let's look at an example of a sulfur oxide here that reacts with water. If we take sulfur trioxide and react it with water, that is going to produce sulfuric acid. Now, an example of a nitrogen oxide that we can use here, we can use dinitrogen pentoxide. So we say that if dinitrogen pentoxide reacts with water, that forms nitric acid. Now, one very important thing that you need to know about the sulfur and the nitrogen oxides is that they are byproducts from burning coal and oil. And what is the effect of these nitrogen and sulfur oxides in the environment? They are air pollutants, and when they react with water, they form acid rain. So air pollution with sulfur oxides and nitrogen oxides leads to acid rain. So if you look at this statue here, you see that it is degrading. It's because it's been exposed to rain that is acidic. Now, let's look at the concentration of acids and bases. Here, we have a strong acid, and the strong acid can dissolve lead. So there is lead here that we introduce here. Strong acid will be able to dissolve lead. Now here, we have weakly acidic solutions of buffalo wing sauce and soda, which is the Coca-Cola here. So they are weakly acidic, and here the strong acid that can dissolve lead. Now, how can we say why this one is considered a strong acid and these other ones are considered weak acids? Now, for us to be able to explain this, we are going to start with pure water. So pure water is what we are going to analyze first before we get into explaining strong acids and weak acids in terms of concentration. Now let's look at the self-ionization of water. So this is also called the auto-ionization of water. So we have water here being ionized to give us the hydronium ion and the hydroxide ion. So we could also have it as water ionizing to give us the hydrogen ion and the hydroxide ion. So it's very important to note that in pure water, 1 out of every 560 million water molecules is ionized. Now, if we look at the second example here, if we look at the self-ionization of water here to give us the hydrogen ion and the hydroxide ion. The concentration of the hydrogen ion is equal to 1 times 10 to the minus 7. And the concentration of the hydroxide ion is equal to 1 times 10 to the minus 7. So if we take the product of these two, the product of the concentration of the hydrogen ion and the hydroxide ion, that gives us 1.0 times 10 to the minus 14. Now, if we add acid to water, this is the self-ionization of water. If we add acid to water, what will happen is that, remember, acid ionized in water. What will happen is that there will be an increase in the hydrogen ion concentration and a decrease in the hydroxide ion concentration. Now, if we add a base to water, remember, water would dissociate to give us the acid and the base. So if we add a base, we are increasing the hydroxide ion concentration and decreasing the hydrogen ion concentration. And remember, the product of the hydrogen ion concentration and the base must always be 1.0 times 10 to the minus 14. No matter what happens, if you increase one, the other decreases. They must always give you this product. That shows that what? That the hydroxide ion and the hydrogen ion acts like a seesaw. When one is increasing, the other is decreasing. And when one is increasing, the other is decreasing. Now, let's have a math review here, because we are going to be looking into some calculations to determine whether an acid is a strong acid, a base is a strong base, or is a weak acid or weak base. So let's have a little bit of a math review here. So we are going to look at this standard notation for this number. The standard notation is here is 0.00214. If we take this number and we want to convert it to scientific notation, as we've already seen, we need to move 3 places to the right. And we know that when we move to the right, it's becoming negative. So for scientific notation, we are going to have 2.14 times 10 to the minus 3. Now, how do we call 2.14? 2.14 is called the coefficient. This is called the multiplier. And minus 3 is called the exponent, which is an integer. In scientific notation, the exponent will always be an integer. Now, we can still write this very same number in exponential form. So in exponential form, this same number will be written as 10 raised to the power minus 2.67. So 10 here is called the base, and the power here, the exponent, is called the power here. This is called the exponent. One thing that you have to understand with scientific and exponential form is that for the exponential form, the exponent is not always an integer. So it can be a non-integer. But for scientific notation, it is always an integer. Now, let's look at exponential forms here. You know that if you multiply x to the m by x raised to the power n, that is just exactly the same like x raised to the power m plus n. I show you an example. If you take 5 raised to the power 2 times 5 raised to the power 7, that is exactly the same like 5 raised to the power 9. Now, if you take scientific notation here, if you multiply two scientific notations, what happens is that you multiply the coefficients and then you add the exponents. So that is 1 times 1 gives you 1. Then the exponents you add minus 7 plus minus 7. So that gives you minus 14. So that gives 1 times 10 to the minus 14. Now, let's look at hydrogen ion and hydrogen ions in solution. Remember, we've said the hydrogen ion times the hydroxide ion must always give us 10 raised to the power minus 14. So here, if we have the hydrogen ion here in moles per liter, that's the concentration of 1 times 10 to the 0. Remember, 1 times 10 raised to the power 0 is 1. So here we'll have 1. So if we multiply that, that is the hydroxide ion is going to be 1 times 10 to the minus 14, because their product must always give you 1 times 10 raised to the power minus 14. So if you have the strong acid here with a hydrogen ion of 1 times 10 to the minus 1, the base must be 1 times 10 to the minus 13. If it is 1 times 10 to the minus 3, this other one will be 1 times 10 to the minus 11. So these are strong acids. We know that the neutral point, as we saw for water, is that for the hydroxide ion is 1 times 10 to the minus 7, and for the base, for the hydrogen ion is 1 times 10 to the minus 7. So everything below that is greater than 1 times 10 to the minus 7, that is acidic, and everything below 1 times 10 to the minus 7 here is the basic. So this is weakly basic here, and this is strong basic here, and here this is weakly acidic, and this is strong acidic. Remember, the product of the hydrogen ion concentration and the hydroxide ion concentration must always give you 1 times 10 to the minus 14. We are going to be using this in calculations, so make sure it stays in your brain. Now, let's look at this practice problem. The concentration of the hydrogen ion concentration in an aqueous solution is 1.0 times 10 to the minus 6 molar. What is the concentration of the hydroxide, and is this solution acidic or basic? The solution that has 1.0 times 10 to the minus 6. Is it an acidic solution or a basic solution? Now, we know that the product of the hydrogen ion concentration and the hydroxide ion concentration is 1.0 times 10 to the power minus 14. Here we've been given the hydrogen ion concentration. So we are going to go ahead and substitute it in this equation and equate it to what we have to the right. So we can actually obtain the hydroxide ion concentration here. For us to get that, we are going to divide all through by 1.0 times 10 to the power 6. So the hydroxide concentration is 1.0 times 10 to the power minus 14 divided by 1.0 times 10 to the power minus 6. That gives us 1.0 times 10 to the power minus 8. So we've calculated the hydroxide ion concentration. Now the next question is this solution acidic or basic? We've been told that the solution contains 1.0 times 10 to the minus 6 molar hydrogen ion. So that means the solution is acidic. Looking at our table, that is an acidic value. So from what we've seen that our answer was 1.0 times 10 to the power minus 6. That is in this area. That is around this area here, which is weakly acidic. So this is how you can be able to determine if it is an acid or a base based on the value that you obtain from your calculation. Now let's look at what we call the pH scale. So scientists and chemists have to deal with these concentrations that are confusing. So how do they deal with all these concentrations? Now they came out with what is called the pH scale, and we are going to see what the pH scale is all about. So the pH scale, as we've already seen, will be ranging from 1 times 10 to the power minus to the power 0 to 1.0 times 10 to the power minus 14. That is for the hydrogen ion concentration. And pH is defined as minus the logarithm of the hydrogen ion concentration. So we've been able to calculate the hydrogen ion concentration here. So with the hydrogen ion concentration that we have here, we are going to be able to determine the pH using the formula pH is equal to minus log of the hydrogen ion concentration. So let's see how we are going to deal with numbers and the logarithm. So if you have a number of 10 to the power 18, the logarithm is going to be 18. Now if you have a number of 10 raised to the power minus 2.3, the log, if you punch it on your calculator, you are going to have minus 2.3. So if you have a number like 100, you can also express 100 as 10 raised to the power 2, and it will give you a log of 2. So if you take the log of 100, that gives you 2. Now, if you take 1000, 1000 can be equated the same like 10 raised to the power 3, and the log of that number will give you 3. Now let's look at the log of negative number. Since we've said pH is minus the log, so we are going to look at the minus here. So let's look at minus log. We've looked at log, let's look at minus the logarithm now. So if you have a hydrogen ion concentration of 10 to the power minus 7 minus the log will give us 7. So if we have 10 raised to the power minus 13 minus the log will give us 13. If you have 10 raised to the power minus 5.8 minus the log will give us 5.8. So let's look at hydrogen ion concentration, hydroxide ion concentration, and pH. Remember, we said pH is minus the log of the hydrogen ion concentration. So each time you are talking of pH, you are talking of hydrogen ion concentration. So if you have a hydrogen ion concentration of 1 times 10 to the 0, your pH value will be 0. If you have 1 times 10 to the power minus 1, your pH value will be 1. If you have 1 times 10 to the power minus 3, your pH value will be 3. And remember, the product of the hydrogen ion concentration and the hydroxide ion concentration must always be 1 times 10 raised to the power minus 14. So that is the same thing for all the table here. So when the hydrogen ion is greater like 14, we are talking about strong bases. And when it is small, very small here, close to 0, we are talking about strong acids. And the neutral point here, that is for water. So everything up here is for acids. So strong acids, the strength of the acid goes this way. And for bases, the strength of the base moves towards this way. Now, let's see how we can look at pOH. Since we've said pH is minus the log of the hydrogen ion concentration, as well, pOH is minus the log of the hydroxide ion concentration. So that is the same, pH minus log of hydrogen ion concentration, pOH minus log of hydroxide ion concentration. So we know that the hydrogen ion concentration, the hydroxide ion concentration must always be 1.0 times 10 to the minus 14. So pH plus pOH will always give us 14. So how do you get pH minus the log of hydrogen ion concentration? So if you take the logarithm of both sides, you have minus log of hydrogen ion concentration plus log of minus log of hydroxide ion concentration to give us minus the log of 10 raised to the power minus 14. That will give you pH. We know that minus the log of hydrogen ion concentration is pH, minus the log of the hydroxide is pOH, and we have 14 to the right. So there are 4 equations here that relate hydrogen ion concentration and hydroxide ion concentration. Make sure you remember all these 4 equations because we will use them to solve all pH problems and concentration of hydrogen and hydroxide ions. So the first equation is the hydroxide ion times the hydrogen ion must be equal to 1 times 10 to the power minus 14. The second equation is pH is equal to minus log of hydrogen ion concentration. pOH is minus log of hydroxide ion concentration, and pH plus pOH is equal to 14. Always remember this. Now let's look at an example. A chemist measures the acidity of a solution and finds that the hydrogen ion concentration is equal to 0.01 molar. What is the pH of this solution? Next question. Is the solution acidic or basic? Now let's see how we can solve the problem. We know that the hydrogen ion concentration is 0.01 as we've been given. So we can also state this formula, this value in scientific notation. So if we have to put it in scientific notation, we're moving 2 places to the right. That is going to be 1 times 10 raised to the power minus 2. Now, if we want to put it in exponential form, that is going to be 10 raised to the power minus 2. So the next thing is pH. We know that pH is minus the log of the hydrogen ion concentration. So if you take pH of minus 0.01, looking at the scientific notation here, you will know that the answer is going to be 2, and that is acidic. So is the solution acidic or basic? 2, and it is acidic. So the pH scale, when we look at the pH scale here, we have the neutral position here 7. From here we have 8, 9, 10, 11, 12, 13, and 14. So it increases in this direction. And here to this other direction, we have 6, 5, 4, we have 3, we have 2, and we have 1. So the pH scale runs from 1 to 14, and 7 is the neutral point. Anything to the left is acidic, and anything to the right is basic. So an acid with a pH value of 1 is acidic than an acid with a pH value of 2. So an acid with a pH value of 1 is more acidic than an acid with a pH value of 6. So these ones here are just weakly acidic around the neutral point. The acids and the bases around the neutral point here, they are weakly acidic and weakly basic. Now let's look at another example here. A solution of hydrochloric acid in water is found to have a hydrogen ion concentration of 0.0030 molar. What is the pH of this solution? You could just go ahead and calculate it, or we can start by estimating it. Now, if we want to estimate the value, we know from our table that if we look at these values here, 0.100 is the same as 10 raised to the power minus 1. So if we move here, that is 10.0. That's 10 raised to the power minus 1. That's the exponential. So this is 10 raised to the power minus 2. And this is 10 raised to the power minus 3. The pH value here is 1, here is 2, and here is 3. Now, if we want to estimate 0.0030, we are seeing that 0.0030 would be equal to 3. So this is 1, 2, 3. 3.0 times 10 raised to the power minus 3. So 10 raised to the power minus 3 is somewhere here. This is it here. So 3 times 10 raised to the power minus 3 is greater than that. Remember, minus 2, 10 raised to the power minus 2 is greater than 10 raised to the power minus 3. That's very important. 10 raised to the power minus 2 is greater than 10 raised to the power minus 3. So 3 times 10 raised to the power minus 3 is going to be somewhere here before 10 raised to the power minus 3. So we see that our pH value is going to be between 2 and 3, somewhere here. Now let's go ahead and calculate the pH value. So if we want to calculate it, we have the concentration of 0.0030, and we know that pH is minus the log of the hydrogen ion concentration. So we put minus log of 0.0030, and that gives us a value of 2.5. Now let's look at this other example involving carbonated drinks. Carbonated soft drinks are fairly acidic and typically have a pH of about 3. What are the hydrogen ion concentration and the hydroxide ion concentrations at this pH? So what you see here is that we have been given the pH value, and we are asked to calculate the hydrogen ion concentration and the hydroxide ion concentration. So the first thing that we are going to state is that pH that we've been given is given by minus the log of hydrogen ion concentration. Now, from the pH, how can you obtain the hydrogen ion concentration? This is very important. So hydrogen ion concentration is given by 10 raised to the power minus pH. Keep this formula at the back of your mind. Don't forget this formula. How do you obtain the hydrogen ion concentration from the pH? The hydrogen ion concentration is obtained from the pH by the formula hydrogen ion concentration is equal to 10 raised to the power minus pH. So we've been given the pH of 3 here. So to obtain the hydrogen ion concentration, it is going to be given by 10 raised to the power minus 3. So that is equal to 0.001. Now, how can we calculate the hydroxide ion concentration? Now we have the hydrogen ion concentration. How can we calculate the hydroxide ion concentration? We know that the hydrogen ion concentration times the hydroxide ion concentration is equal to 10 raised to the power minus 14. So we just calculated the hydrogen ion concentration, which is 10 raised to the power minus 3. So we go ahead and substitute it here and calculate the hydroxide ion concentration. So the hydroxide ion concentration is 10 raised to the power minus 14 divided by 10 raised to the power minus 3. That gives us 10 raised to the power minus 11. So we have the hydrogen ion concentration and the hydroxide ion concentration. With the hydrogen ion concentration here, we can calculate the pH. If you take the pH, you are going to obtain 3, which is exactly what we are given. So we can also calculate the pOH here. The pOH here is minus the log of the 10 raised to the power minus 11, which is 11. So we have hydrogen ion concentration 10 to the minus 3, hydroxide ion concentration 10 to the minus 11 molar. Now, what is the hydrogen ion concentration in an aqueous solution with a pH of 9.43? In the previous slide, we said we can obtain the hydrogen ion concentration from the pH by the formula hydrogen ion concentration is equal to 10 raised to the power minus pH. So hydrogen ion concentration is equal to 10 raised to the power minus pH here. And that gives us a value of 3.72 times 10 to the minus 10 molar. How can you get this value from 10 raised to the power minus 9.42? On your calculator, the easiest way for you to get this number from here is on your calculator, you press minus 9.43, then you press second function and log. That gives you this value. So this is the exponential and this is the scientific notation. Now let's see how we can measure acids and base concentrations. So for us to measure acids and base concentrations, we can use what is called pH indicators. And what are pH indicators? pH indicators are compounds that change color depending on the pH. So we have the very first pH indicator here is litmus. Litmus is one of the oldest ways and it is used to identify an acid or a base. So for litmus, we have red litmus paper and blue litmus paper. So how do you identify an acid or a base? If you place a blue litmus paper into an acid, it will turn red. And if you place a red litmus paper into a base, it will turn blue. So what you see here, this is red litmus dipped into this base. Since it is blue, it means that this solution is a base because it has turned the red into blue. Now, we also have what is called the pH paper. The pH paper actually gives us more information about the pH value because the pH paper contains colors here, and when you dip your litmus paper into the solution, you can actually compare with the color that you have, and that gives you an estimate. Now, another indicator that we can use, another pH indicator, is called phenolphthalein. Phenolphthalein is a pH indicator that is colorless in acid and it gives a bright pink color in base. So if you drop phenolphthalein into acid, it is colorless, but if you put it into base, the base becomes pink. So another way, which is the most accurate way of determining the pH, is with the use of pH meters. So a pH meter precisely measures the pH. Now let's look at what we call acid-base titrations. What are acid-base titrations and why do we carry out acid-base titrations? Acid-base titrations are titrations between an acid and a base. Now, why do we use acid-base titrations? So acid-base titrations are used to precisely measure the concentration of an acid or a base. Now, how is that done? To measure the concentration of the acid, this is the procedure that we are going to follow. The first step is that we are going to prepare a basic solution of a known concentration. Now, in chapter 10, in solutions, we described how we can prepare a solution. That is very important. Now, the second step is to measure the volume of the acid and add an indicator. We are going to use a pipette to measure the acid and then put the acid into an Erlenmeyer flask and then add 2 to 3 drops of phenolphthalein. Now, the third step is that we have to fill the burette with the basic solution that we've prepared. So this is a burette here. We are going to fill the burette with the base that we've prepared, and then we are going to titrate against the acid. So the fourth step is that we add base until acid is neutralized, and that happens when we have a slight pink color, and that persists. So here we have the titration going on, the acid-base titration. We have our base in this burette, and we know the volume in the burette. And at the end of the titration, we will be able to determine the volume of the base that we've used. And we already know the volume of the acid that we measured. We also know the concentration of the base that we prepared. And we added 2 to 3 drops of phenolphthalein. Now, what happens when the reaction is complete? For you to know that the reaction is complete is when, remember, you added the phenolphthalein into acid and it was colorless. Now, when you keep adding the base, when the neutralization has taken place, any drop of base is going to give a permanent pink color to the solution. And at that point, that is the end point of the titration. So the titration adds just enough base to neutralize the acid, and this is what you will obtain at the end point. So this is the reaction that takes place. If we are reacting hydrochloric acid with sodium hydroxide, that gives us sodium chloride and water. Now, the moles of hydrochloric acid here are equal to the moles of sodium chloride. So 1:1. So we know that from chapter 10 that moles is given by the molarity times the volume. So the moles of acid here is equal to molarity of acid times volume of acid, and the moles of base here is molarity of base times volume of base. So we can use this formula to be able to determine the concentration of the acid, because we have the molarity of the base that we prepared, we know the volume of the base that we have used, read from the burette, and we know the volume of the acid that we used in that titration. So we are going to make the molarity of the acid here the subject, and we calculate that value. So if we do that, molarity of acid is given by molarity of base times volume of base over the volume of acid. So that will help you to determine the concentration of the acid. Now let's look at an example. A 25.0 milliliter sample of hydrochloric acid is neutralized by the reaction with 17.4 milliliters of 2.00 molar sodium hydroxide. What was the concentration of hydrochloric acid in the unknown sample? So here we have 25.0 milliliters of hydrochloric acid, we have 17.4 milliliters of base, and 2.00 molar sodium hydroxide. Let's collect the data. We know that the moles of acid is equal to the moles of base because we said hydrochloric acid and sodium hydroxide react in a 1:1 ratio. What are the informations that we have? We have the molarity of the acid. We know that this is the formula that we will need to use. So let's collect our data. We have 25 mils for the volume of the acid. We have 17.4 milliliters for the volume of the base. And we have 2.00 molar for the base. And the molarity of the acid is not known. So from this formula, we can calculate the molarity of the acid, which is molarity of base times volume of base over volume of acid. Now we are going to substitute these values that we have here, and that gives us 2.00 times 17.4 milliliters over 25 milliliters. So we see that the milliliters here will cancel with the milliliters, and we are left with molar. So that gives you a value of 1.39 molar. So that is the concentration of the unknown acid. Now, let's look at the case where the coefficients of the acid and the base are different, unlike sodium hydroxide and hydrochloric acid that have the same coefficients of 1:1. Now, let's look at hydrochloric acid reacting with barium hydroxide here. We see that in this balanced equation, we have 2 moles of hydrochloric acid and 1 mole of barium hydroxide. We are not just going to state that molarity of acid times volume of acid is equal to molarity of base times volume of base, because the coefficients are different. Now, how do we state that? Alright, so we are going to divide the moles of the acid by the coefficient and the moles of the base by the coefficient. So the moles of acid by the coefficient is equal to the moles of the base by the coefficient. So C here is the coefficient of the acid, which is 2. CB here is the coefficient of the base, which is 1. So we are going to have molarity of acid times volume of acid over the coefficient, which is equal to molarity of base times volume of base over the coefficient. Now let's look at an example. A 30.0 milliliter sample of aqueous barium hydroxide is neutralized with an HCl solution having a concentration of 0.400 molar. If 22.6 milliliters of aqueous hydrochloric acid are required to complete the neutralization, what is the concentration of the barium hydroxide solution? Now, the first thing is that we have to write out the balanced equation. And here we see that the coefficients are not the same. So we have to determine the moles of each of them. So we have been asked to calculate the concentration of barium hydroxide. So we are going to look at the acid here. We have 22.6 milliliters, that is the volume, and we have 0.400 molar, that's the molarity. So we can determine the number of moles of the hydrochloric acid here. And this is the procedure that we can move. From the volume of the acid, we can convert to the moles of the acid, and the conversion factor is the molarity here. From the moles of acid, we can convert to the moles of the base using the balanced chemical equation, the coefficients, the mole ratios here. Now, from the moles of the base, we will be able to convert to the concentration of the base using the molarity. Now, let's go ahead and do that calculation. For us to determine the moles of hydrochloric acid, we are going to multiply the volume by the molarity. Remember, we said concentration, which is molarity, is equal to moles over the volume. So to determine the moles, we multiply molarity by volume. So we have 22.6 milliliters and the molarity is 4.00 mole per liter. Remember, molarity here is moles per liter, and the volume here must also be converted to liters. So we have 0.400 mole per liter times, if you have to convert 22.6 milliliters to liters, you have to divide by 1000, and that is going to give you 0.0226 liters. So liters cancel and we are left with moles. That gives us a value of 0.00904 moles of hydrochloric acid. Now, we are going to use the balanced chemical equation to convert from moles of hydrochloric acid to moles of barium hydroxide. And we are going to use the coefficients in the balanced equation. So 0.00904 moles of hydrochloric acid times, we see that for every 2 moles of hydrochloric acid, 1 mole of barium hydroxide is used. So for the conversion factor, moles of hydrochloric acid will be at the bottom, which is 2 of them. So times 1 mole of barium hydroxide over 2 moles of hydrochloric acid. That gives us a value of 0.00452 moles of barium hydroxide. Now, we have the moles of barium hydroxide and we have the volume, and we are now looking for concentration. So we have moles and volume, we are looking for concentration. So concentration is equal to moles divided by volume. So we are going to divide the 0.00452 by the volume. Remember, the volume here is in milliliters and we must convert it to liters. So the concentration is going to be 0.0045 molar divided by 0.0300 liters. We have converted this to liters. That gives us a value of 0.15 molar barium hydroxide. Now let's look at a second example. A chemist needs to completely neutralize 0.600 liters of a 3.0 molar aqueous sulfuric acid solution. What volume of 0.80 molar aqueous potassium hydroxide is necessary to do this? If the chemist adds 5.0 liters of aqueous potassium hydroxide to the acid solution, will the resulting solution be basic, acidic, or neutral? So here we have the volume of acid, we have the concentration of the acid. Here we have the concentration of the base, and we are looking for the volume. Now we have to write out the balanced chemical equation first. So we see that for every 1 mole of sulfuric acid, 2 moles of potassium hydroxide are used. So we can calculate the moles of sulfuric acid, then convert it. Now let's go ahead. The moles of sulfuric acid is going to be given by molarity times volume, and that is 3.0 times 0.006, 6.00 liters. Now that gives us a value of 1.8 moles of sulfuric acid. Now we look at the balanced equation. We have to convert moles of sulfuric acid to moles of potassium hydroxide. So we are going to use the conversion factor here. For every 1 mole of sulfuric acid, we have 2 moles of potassium hydroxide. So 1 mole of sulfuric acid will be at the bottom and 2 moles of potassium hydroxide at the top. So the moles of sulfuric acid cancels, and we are left with moles of potassium hydroxide. Now, from the moles and the molarity, we can calculate the volume. So the conversion factor is that we have 0.80 moles per liter. So we are using that conversion factor here. We see that the moles cancels out, and we are left with the liters. That gives us a value of 4.5 liters of the base that are used. Now the next question is this solution acidic or basic or neutral? So we've seen that we need just 4.5 liters of the base, but how many liters did we add? We added 5.0, so there is an excess of the base. So if 5.0 liters of potassium hydroxide are added, the solution will be basic, because we needed just 4.5, but we added 5, so the solution will be basic. Now let's look at what we call buffers. So for buffers and biological pH, the cells that make up our skin, muscles, and blood and organs, they must remain in a very narrow pH range in order to function properly. The fluid inside the cells typically maintains a pH of about 6.8, while the bloodstream maintains a pH very near to 7.4, given the number of acidic and basic components present in the bloodstream and inside the cells. How do our bodies remain within these ranges? For our bodies to remain within these ranges, they use what is called buffer systems to keep the pH at healthy levels. So a buffer is a solution that does not change when we add small amounts of acid or base. So a buffer solution will resist changes in pH when we add small amounts of acids and base. Now let's look at how this happens. Let's start with pure water here. So we have pure water, pH 7. If we add acid to pure water, we see that the pH will rapidly change. If we add a base to pure water, we see that the pH will rapidly change. Now let's come to buffer solutions. I want you to see what happens with buffer solutions. We've said buffer solutions, these are solutions that resist changes in pH. Now, if we add the same amount of acid that we added to that pure water, if we add it to a buffer solution, we see that the pH here will be 6.88. So it changes just very slightly. And if we add a base, we see that the pH will change just very slightly. So that is how buffers work. They are resisting changes in pH. So our systems, they have buffers that resist changes in pH. Now, how are buffer solutions made? So for the composition of a buffer solution, it is composed of a weak acid and its conjugate base. That is for an acid buffer, because we have acids and basic buffers. So an acid buffer contains a weak acid and a salt of its conjugate base. So weak bases will also be combined with their conjugate acids to form the buffer. This is the base buffer. So we have acid buffers and basic buffers. For example, here in the system of most organisms, there is this ion and its conjugate. So we have the dihydrogen phosphate ion here and the hydrogen phosphate. So this is a pair. So when we add acids or bases, this is the pair that is going to maintain or resist that change in that pH. How do they work? We are going to see in a few slides. So we have the dihydrogen phosphate here in water. So this is the conjugate base. So what happens in aqueous solution is that if you add any acid, if you add any base, this is going to be consumed by the excess. This is going to be consumed by the dihydrogen phosphate. So the dihydrogen phosphate here has the role of consuming any base. Now, this is the conjugate here, and what happens is that it will consume any acid that is present. So any excess acid will be consumed by this. So if you add acid, it will be consumed by the hydrogen phosphate. And if you add any base, it is going to be consumed by the dihydrogen phosphate. So what happens is that the ratio of the dihydrogen phosphate and the hydrogen phosphate will change, but the pH will not change because they will consume any acid or any base that is added. So that is how the buffer solutions work. Now, let's look at the analogy of this situation to real life, what you can see. So this is the one that is consuming the excess acid, and this is the one that is consuming the excess base. So the acid-base pairs, so for the conjugate, they are just like guard dogs. So you have one guarding the other direction and one guarding the other direction. So if there is anything coming from this direction, let's say excess acid, excess base, it will be consumed by this one. And if there is anything coming from this direction, which is the excess acid, be consumed by this other guard dog. Now, let's see, blood contains a carbonic acid and bicarbonate buffer. So the carbonic acid here and the buffer here, they will work just like we have explained. So if there is any base, the base will be consumed by the carbonic acid. And if there is any acid that is added, the acid will be consumed by the ion here. So that is how they work. Now, how are buffers used in solutions? So buffers can actually be overloaded. So if you overload a buffer, for example, if you add too much of acid, the solution will drastically change to acidic solution. If you add too much of a base, the solution will drastically change to a base. So buffers can be overloaded, and buffers can be adjusted to a specific value that you want.